All right, for today's pre-lecture video, I decided to focus on Kirchhoff's rules, which are one way that we can find the current traveling through a circuit that is a little bit more complicated than just resistors in series and parallel. So basically, the types of circuits that we might be looking at to use Kirchhoff's loop rules might look like this one. Notice this one has two batteries, which immediately just kind of confuses you because you're not really sure, which way's current going to go, which battery's going to win, and, we can't really say for sure what's in parallel, what's in series. So when you see a circuit like this, you can use what we call Kirchhoff's rules. So there are two rules that we're going to really base our method on. The first one is called a junction rule. And so basically, at a junction, when we see it, it's a point where there's sort of a point where different currents are coming together or separating. And so, for instance, this junction has three different paths. And we can imagine maybe some currents coming in from the left and from the right, and then the current flowing down. So whenever we see a point like that, a junction point, we apply what we call the junction rule, which basically says the sum of the currents coming into the junction is zero. And the reason that that works is the ones coming in are treated as positive, and the ones going out are negative. And so, for instance, in this picture, we would have I1 plus I2 minus I3 equals 0. Sometimes I also like to write it as I1 plus I2 is equal to I3, which of course is exactly the same meaning, it just is written slightly differently. So one of the things that we can think about in trying to understand this rule is we could view it as sort of a conservation of charge. That is, as the current is flowing in from the left and from the right into this junction point, and then it comes down through this vertical piece of wire, we could think of that current, of course, as traveling charge, and whatever charge comes into that junction point has to come out. And that's what I mean by thinking of it as conservation of charge. There also is this water pipe analogy, which I think is handy as well. Again, trying to think about the flow of water, and also the flow rate gives that time dependence, which current has, because current is charge per unit time. And so the flow of the water coming into the junction has to be equal to the flow rate of the water coming out. The other rule that we use for Kirchhoff is called the loop rule. And basically, a loop is when we take this circuit again, this one that we looked at the beginning, and we basically just sort of choose a point to begin in the circuit and choose a point to end. And so in this picture, notice that they've shown three different loops. And none is better than the other, they're just different. But the idea is that as you go around the loop, the sum of the potential differences, and that means the potential rises and potential losses, has to add up to be 0. The idea is, of course, as you're going through different elements, so for instance, as I go around loop 2, as I go through the resistor and the battery, and then I come around and go through this battery and this resistor. We'll talk about the rules in a minute, but as I go through those different elements, some will constitute a potential difference which is negative, like a potential loss, while other motions like movements or passing through elements will represent a potential gain, which is going to be positive. The Kirchhoff loop rule basically means that the electrostatic force is conservative, and that what we're saying by that is the work done in a closed loop is equal to 0. Remember, I don't know if you remember back from first semester, we talked about conservative forces. And conservative forces are forces for which, when you calculate the work done, the work done is independent of the path. It only depends on where you begin and where you end. Sort of what results from that is that if you begin and end at the same location, you don't do any work. Sometimes I also think of it as conservation of energy, the idea that as we go through the loop, sort of our net change of energy has to end up to be zero. We might gain a little bit of energy at one point, lose a little bit at another point, but when we get back to where we started, we have to have the same amount of energy. So there are some sign conventions for us to remember as we're traveling around the loop in terms of deciding whether we're going to gain potential or lose potential. So let's look at batteries first. If I'm going around the loop and I travel through a battery from the negative terminal to the positive terminal, that's going to be a potential gain equal to the voltage of the battery. So that's a plus E right there. However, if I'm traveling around the loop and I go through the battery from the positive to the negative in that opposite direction, that represents a potential loss. And so the change in potential there is minus E, where E, of course, is the voltage of the battery. Our second set of rules has to do with traveling through resistors. Now, when we're traveling through the resistors, we have to pay attention to the direction of the current, which, as a matter of fact, we chose, and we choose it, just randomly. We don't really have to think too hard. So in these pictures, we chose for the current to be going to the left through the resistor. Okay, so keeping that in mind, as we're traveling around the loop, if we go through the resistor opposite to the direction of the current, we have a potential gain equal to the current times the resistance. However, when we're traveling around our loop, when we go through the resistor, we're traveling with the current, that actually represents a potential loss. And so the potential change there is minus the current times the resistance. So these are our 4 sets of rules that we have to remember. So let's talk about the steps that we follow when we're using Kirchhoff's rules, and then we'll look at a real simple problem. So the first thing you have to do is you have to look at your circuit and identify the pieces of the circuit where the current will have a particular value and be different from other areas. You want to label each of those branches. You call them I1, I2, I3, and you also indicate what direction you think the current is traveling in. Again, this is one of those situations where it doesn't really matter what direction you choose, because if you get it wrong and you do everything else correctly, you'll get a negative value for your answer. So just choose a direction, don't agonize over it, just do it. The next thing that we want to do is, once we've done that, we're going to use a junction rule to get an equation that relates the currents. That's where you do something like, you look at a point and is it I1 plus I2 equals I3, something like that. So that'll give you one equation. Then you have to find some closed loops. You basically sort of decide on a path that you're going to follow in the circuit. Once you've done that, you're going to use the loop rule to write the equations that relate the potential gains and losses in the loop that you choose. That's where you're going to use the rules that we were discussing previously. The ones where you're going through the battery or through the resistor. So your goal is that you need to figure out all your unknowns, and so you need as many equations as you have unknowns. A lot of our problems will have 3 different currents that we're trying to find, and so we need 3 different equations. Our junction rule will give us one equation. Unfortunately, if you use another junction, often it'll give the same basic equation. So you usually can only use the junction rule for one equation. And then you have to choose 2 loops to give you the 2 additional equations. Those are the loop rules relating to the changes in potential. Then if you have 3 equations in all, you just do the algebra and solve for your unknowns. So let's look at an example. Okay, so here's an example where we have 2 batteries, a 10-volt battery and a 5-volt battery. And then we also have two resistors, a 30 ohm resistor and a 20 ohm resistor. Now I see three different areas where the current could be different. In this left-hand portion of the circuit, that's where the current would have a one value, and I'm going to call that I1. In the middle, there's another value for current, and I'm going to call that one I2. And then finally, in the right-hand side, I have I3. Now, if I look at this junction point, I have I1 coming into it, I2 going out, and I3 coming in. And so my equation for my junction rule would be I1 plus I3 is equal to I2. So that's one of my equations. Now I'm going to choose some loops. And I'm going to first choose a loop in the left-hand side. That's loop 1. And so when I go around loop 1, I'm going to start at the battery and I'm going to go in this direction. So I go through the battery from negative to positive, so that's a potential gain of 10 volts. Now I'm going to follow all the way around, and now I'm going to come through the 30 ohm resistor in the direction of the current I2. So that's a potential loss of minus 30 times I2. And then I continue around the loop and I get back to the battery, so I'm all done, and so that's equal to 0. So that's one of my equations. Now for my second loop, I'm going to go around like this, and that'll be loop 2. And again, I just chose the direction, so I started at the battery and I went from negative to positive, so that's a potential gain. I'm going to go through the 20 ohm resistor with the current, so that's a minus 20 I3. I come down through the middle through the 30 ohm resistor in the direction of current 2, and so that's another loss, minus 30 I2 equals 0. So I have 3 equations and 3 unknowns. And so I should be able to solve for everything. Now this one was actually, I was pretty lucky. This equation right here is pretty easy to solve. I get 10 minus 30 I2 equals 0. 10 is equal to 30 I2. I2 is going to be 10 over 30, or just 1/3. That one was easy. So usually the algebra is a little bit more involved. Now I'm going to take that value and I'm going to put it into here, and what I get is I get 5 minus 20 I3 minus 30 I2, which is 1/3, equals 0. So I got 5 minus 20 I3 minus 10 equals 0. So I get minus 5 minus 20 I3 equals 0. And so minus 5 equals 20 I3. So I3 is going to be equal to minus 1/4. Now what that does is that tells me that the direction of current 3 was incorrect. And so now I know that actually current 3 actually goes in this direction. But that's okay, because everything that I did was based on that direction of current. I have to keep that negative value. And so now I have I1 plus I3 equals I2. This is going to allow me to solve for I1. I1 is equal to I2 minus I3. And so I2 is 1/3 minus I3, but that was minus 1/4. So I get 1/3 plus 1/4. And this ends up to be 7/12, which is equal to 0.583 amps. And that is how we can use Kirchhoff's rules to solve the current in a simple circuit that didn't look like we could tackle it with series and parallel.